Hello class, this is Ms. Riggins with today's video on section 2.4 Composite and Inverse Functions. As you're watching the video, please feel free to take notes, writing down important information as well as statements or questions that you may have. Don't forget to, at the end of the video, write the summary and submit the summary in the WISC via online. Please feel free to pause or rewind the video as you need to, or replay the video as many times as you need to. Let's begin. Today we're going to be talking about composite and inverse functions. First, let's take a look at what composite functions are. So suppose I have two functions. I'm going to call them f and g. And f and g both have their own respective domains and ranges. But let's say that I want to take values from the domain of f, and I want to input them into f, and I'm going to get out values into the range of f. Okay? And let's say I want to take the values from the range of f and input it into G, and when I get the result will be outputs from the range of G based off the inputs, which are the ranges of f. Confusing, isn't it? But that's what composite functions are. They're basically a result of combining two functions, not by adding, subtracting, or multiplying or dividing, but taking the outputs of one function and using them as the inputs of another function. And we call that resulting function a composite function. In this case, we use the symbols G, little circle, F, which means I put into G F. So this terminology also means the same thing, except we don't use curly brackets. We use another set of parentheses. Okay, so here we have now a third function, which we call the composite function, G compose F, because I put into G the output values of F. Let's take a look if we do it the other way around. So let's say here we have two functions, F and G, and we start with the domain of G, and we take an X value from the domain of G, and we put it into G, and the resulting output is a member of the range of G, and we call those output values G of X. And then we're going to take the output values of G that are also in the domain of F, and we're going to put them into F, and the resulting output values will be called F of G of X, or the composite function F of G of X. So now we have a third function, f compose g, or the composite function f and g, such that the inputs of f are the outputs of g of x. Now to differentiate between the different functions, because we have actually three functions that are part of it, we call the inside function, in this case, g of x, and we call the outside function, and we call f the outside function. Okay, so over here in our previous example, the inside function in this case is f, and the outside function is g. So your book defines for two functions f and g, the function f of g of t is said to be the composition of f with g. So the function f of g of t is defined by using the output of the function g as the input to f, which is this example up here. Now let's see how we can come up with a way to describe the composition function algebraically. So here we have two functions, f of x and g of x. And then what we're going to do is we're going to look at the composition of f with g. In other words, where g is the inside function and f is the outside function. And so that terminology or that notation is indicated as such, and these two mean the same thing. This one is easier for me as well. So what this means is I'm going to put inside the inside function is g of x, and I'm going to put that inside f of x. So if you recall, g of x is equal to x over x minus 3. So I'm going to put that into my outside function f. So how do I input that into f? Well, if you take a look over here, the outside function f of x takes its input and adds 2 to it and puts in the denominator of this function. So what I'm going to do is I'm going to take my input, which is x over x minus 3, and I'm going to put that in my input, add 2 to it, as you can see, and put that in the denominator with 1 in the numerator. That's all I do when I compose. I use the input for the outside function and replace the input for the outside function with the output of the inside function, which is exactly what I did here. And then the rest is a result of simplifying using algebra to get a simplified answer. And my simplified answer, as you can see, is this. And this function is the same as the composite function f of g of x, as you can see. Let's take a look at another example. Now in this particular, so I have another set of functions, f of x and g of x, and I'm going to look at f composed g. As we can see, either of these in notations is correct. So in order to do that, I'm going to need to determine what g of x is and put it into f of x. So in other words, since g of x, which is my inside function, is 2x minus 1, I'm going to place into f of x 2x minus 1 as my input instead of just x. And what does f do with its inputs? Well, as the outside function, what f does with its inputs is it takes its input and it takes 2 plus 3 of x, and it multiplies 3 times your input, and it takes the square of your input and squares it and adds them all together. So that's exactly what we're going to do here. We're going to take, for our resulting output for f of g of x, is going to be equal to 2 plus 3 times the input, which is g of x plus x squared, where x in this case is g of x squared. And so we end up with something like this. As you can see, the 2x minus 1, which is the g, which is in here, and then we're going to square it. So the resulting function, when I do my algebra and simplified, looks something like this. So this function is essentially simplified the composition function of f of g of x. All right, in the class we're going to talk about the domain and ranges, because what's going to happen is if I'm going to put g into f, I need to make sure that the outputs of g are part of the inputs of f, or they're part of the domain of f, and I have to make sure that the outputs of f are part of the inputs of g. And we'll talk more about that in class. Now let's take a look at inverse functions, which is a little bit easier. So here we have an example of 2 boxes of functions, f and its corresponding inverse function, and we notate that by f with the power of -1. So how is f inverse related to f? Well, if you take a look here, we see that we have apples. F takes apples and produces as its inputs and produces lemons as its outputs. And F inverse takes lemons as its inputs and produces outputs of apples. And even more specifically, if we take a look at this particular function, the first apple that went in was apple A, and outputted the first lemon, which is lemon 1. The first lemon into the inverse function was lemon 1, and it outputted the first apple out, which is apple A. Let's see if that pattern continues. The second apple in to function f was B, and it resulted in lemon 2, and then inverse function took lemon 2 and it paired it and it outputted it with apple B. Do you see a pattern? Let's see. Apple C goes into F and comes out a lemon 3. Lemon 3 goes into F inverse and it comes out as apple C. So in other words, if f of x produces an output y, then the inverse function, f inverse, when it inputs y, it produces the corresponding output x. So in other words, the functions f and f inverse are called inverses because they undo each other when they're composed. Yes, inverse functions can be composed into f into f function. So let's take a look at that, what I mean by that. So the relationship between f inverse and f is that when I compose each of them within one each other, if whatever the input is after the composition functions resulting will be the same, the output will be the same input, and vice versa. And we'll take a look at what that means with some examples. And it doesn't matter if I compose f inverse with f or if I compose f with f inverse, it's still going to give me the same relationship between the two. If we take a look at the domain and the ranges of f and f inverse, if the domain of f is x, big X, then in the domain of in the range of f is big Y, then consequently the domain of G, what did I say, G? So the domain of f inverse is the same as the range of f, and the range of f inverse is the same as the domain of f. Okay? And that's important to note. Both of these statements are very important to note. Let's take a look at what that means in another. So here's an example. Let's say f is a function where f of 2 is equal to -5. Well, then if f inverse exists, then f inverse of -5 is going to give me back my original x. And that's the relationship that holds right over here. What does that mean graphically? Well, what that means graphically is that they're basically reflections of each other across the line y equals x. And the reason why is that here, whatever xy is, this is going to be yx. It's an opposing thing on the opposite side. So inverse functions are reflections of each other across the line y equals x. Inverses of each other, as we can see. Now, it's important to note that a function can have an inverse, but the inverse is not necessarily a function. So let's take a look over at this particular example. We have the function f of x, and then when we take a look at the reflection line y equals x, we end up with the blue graph, which is a reflection of the f of x over the line y equals x. But as you can see, the blue graph has a problem because for each input, you're going to have more than one output. It means it fails the vertical line test. So all that means in this case is that this function's inverse is not a function, whereas this function's inverse is a function because it passes the vertical line test. For each input, there's only one output on the line f inverse of x. Okay. A good way to determine if a function has its inverse before graphing the inverse relationship is, instead of the vertical line test, it's called the horizontal line test. So remember, in the vertical line test, a relationship fails to be a function if it intersects a vertical line more than once. Well, in the inverse test, a function does not have an inverse function, even though we'll have an inverse relationship, if it fails the horizontal line test. So in this case, if I make a horizontal line and it intersects the original function in exactly one spot, then the function does have an inverse function. But if it intersects the spot in more than two spots, then it's not, in two or more, then it's not, the function does not have an inverse. So if we take a look at this function, like here's my f of x, and I'm particularly testing this function. And I take a look at my horizontal line test. As you can see here, each horizontal line that I draw will only intersect the graph f of x once. But if I do the f of x horizontal line test over here, as you can see, the functions, the horizontal lines are being intersected by the function in two spots. So that's why this horizontal line test will test whether or not a function will have an inverse that is a function. All right, that's it.